Good morning, class. So I hope you had a great weekend, and today we're going to talk about the exam. We're going to debrief a little bit about the exam you took last week, and we're going to do some work with Newton's second law and looking at two specific scenarios. So we'll look at a person in an elevator and try to explain that experience, and we're going to look at a frictionless cart rolling downhill. Okay, so that's what we want to accomplish today. Oh, we'll also look at one of your homework problems, which is actually a kinematics problem. It's a good place to sort of wrap up the unit for kinematics for now. Okay, so that's what we're going to do today. So, good morning. Hi, Steve, Chris, Mike, Holly, Chris, William. Exam. So I graded them and posted the grades. You know what? I'm not sure if I release the grades. Hold on. I'm going to go to Sakai quick here and see if I release the grades. Hi, Kaylee. So let's see. Enter student view. Where's... So it looks like I haven't finished setting up the grade book yet. All right, I'll do that right after class today. Okay, so maybe you can't see your grade yet or see your feedback yet, but I'll do that right after class today. All right, sorry about that. I missed the step. So they're all graded, and the overall score is good. So that's what I'd say. The overall score is good. And what does that mean? Could be better. Could be worse. It's good. In my overall impression of the novel approach to taking an exam is that this Sakai-based Zoom proctored exam was, all things considered, I think it went pretty well. I think you guys handled the situation pretty well. With few exceptions, everybody had great success uploading images or scanned copies of their written work. So I think it went really well. There was some weirdness with the images that were embedded in the exam. My best guess at what caused that was that I put those images in as PNGs instead of JPEGs. And there was some compatibility issues with the browsers not being able to interpret what those files were. So in the future, all images will be JPEGs, and I think that, well, once I posted those pictures as JPEGs into that folder on Sakai, nobody told me that they weren't able to see them. So I'm guessing that's a better format to use. So some of the pictures that were attached were a strange format. They were HEIC. They had the file extension HEIC, and so my computer didn't know that they were images, but it opened them fine once I told it was an image. So I don't know. I guess maybe that's, I don't know. Is that iPhones? iPhones taking pictures that are HEIC format? I don't know. There was quite a few of you who had that. So that wasn't really a problem, and some of the pictures were rotated 90 degrees, so I had to turn my head a little bit to see your work. Not a big deal. So when the grades are released, this is what you'll see. You'll see your score, but you should also be able to see feedback. And I put comments next to the quantitative problems. And those comments include an explanation of what was incorrect if I took points off, and how many points I took off for various aspects of the problem. So you should review that. And then I also, and this you should be able to see now, I have posted written solutions to the exam. So they're on Sakai already under course resources, exam 1. There's a PDF of solutions for the first exam. So you should spend some time, go back and review this exam, because the final exam will be cumulative, so you'll see that at least some of this material again at the end of the semester. Could be exactly the same question in some cases. It could be slightly modified versions of things that you've seen before, or something that was in the homework and wasn't necessarily on this test. All right. Let me see, I got a question here. If you have a file that you know for sure is an image but doesn't have an image file format, you can either rename it or go to File Properties and change the extension to PNG or JPEG. Yeah, I got you, Tyler. Essentially I just told my computer, open this with Preview. I got a Mac. Open it with Preview, and it worked. So I didn't have any, with the stuff that you guys posted, I didn't have any problems viewing what you posted in the end. Any significant problems, I'll say. So it was a learning experience for me. It was a learning experience for you, but we did great. And so next time we do an exam, it'll be the same way. All right. Okay, so let's turn our attention to Newton's laws, and let's go to Chrome. So I'm going to take a look at this problem here. This is in the homework assignment that's due this week. And this problem, it's set up, it's in this unit on Newton's law, Newton's second law, but it turns out this isn't really a Newton's law problem. It's about a sprinter, Andrea. She's 62 kilograms. You're given knowledge about her mass, but you don't really need to know that to solve this problem. She starts a race with an acceleration of 3.2 meters per second. She accelerates at that rate and then maintains that velocity for the remainder of the 100-meter dash. What is her time in seconds? What will her time be for the race? So this problem has, the approach to this problem should involve thinking about it as two parts. The race is two parts. There's the first part where she's accelerating, and then there's the second part where she's moving with constant velocity. And so you think of this as two kinematics problem. One begins at the start of the race and ends after that first interval, and the second one begins after the end of the first interval and ends at the finish line. And your goal then is to figure out how long each of these parts takes and then add them together to get the total time. And so let's try to do this. Okay. Uh-oh. Come on back. Computer. Okay. So, one thing I will say about the exam is you guys should get in the habit of drawing pictures and also defining coordinate axes with your problems. And for the problems on the exam, that wasn't always necessary in order for me to determine what you were up to, but it will become increasingly necessary, especially in when we're using Newton's laws for problem solving. So when we draw a picture here, so here's Andrea. And she's got long legs. And she's running this race. She starts from the starting line, goes for a time, reaches some point, and then runs to the finish line, which is 100 meters. And so breaking it up into two parts. So this first part is where she's accelerating at 3.2 meters per second. So the acceleration in this first part, I'll call that A1, is 3.2 meters per second squared. And her acceleration in the second part of the race is 0. She just moves at constant velocity during that part. And part of the problem was cut off when I showed it to you. Let me zoom out. Oop. Where? Okay. So there's the part that was cut out. She accelerates at that rate for 12.5 meters and then maintains the velocity for the rest of the trip, rest of the race. So x1 is known to us. It's 12.5 meters. Okay, so setting this problem up, think of it as two parts. In this first part of the race, from the starting line to 12.5 meters, the things we know are x naught, x final, which is x1 in this case. We know the rate of acceleration. We know she starts from rest. That's how races begin. You start from rest. And the thing you want to figure out is, well, you need to know how fast she's going at the end of that interval, because that'll be important for the second part, and you want to know how long that part of the race takes. And there's a number of ways you can proceed. You could try to find the time first, or you could try to find the final velocity of this first part of the race first. And I did the latter. I recognized that one of my kinematic equations of motion looks like this. So putting in v1s and x1s and x naughts and v naughts and accelerations, I can solve for v1. It's the only thing in this equation I don't know. And I got 8.944 meters per second. Then, once I know that, I can use this kinematic equation of motion to find T1. And I solve for T1 and I get 2.795 seconds, keeping a few extra decimal places. Okay, so I found two pieces of the puzzle that are going to be important to ultimately answer how long the race takes. I know how long the first part takes. So I didn't use Newton's law at all. It's just kinematics. And the reason I needed to find this part is because when I turn my attention to the second part of the race, now what I know is my initial velocity and my final velocity. In other words, my average velocity for that portion of the race, because acceleration is 0. So her velocity is constant during that part of the race. So all that above there is true because this is true. Acceleration is 0. My initial position is 12.5 meters. My final position is 100 meters. So I can figure out my displacement. And so if what I want is t, the easiest path to finding how long it takes to finish the race is recognizing that average velocity is a displacement over time. So rearranging, time is displacement over average velocity. So that's going to equal x2 minus x1. That's the displacement for the second half of the race, divided by v bar. So now I know it all, and that is 9.783 seconds. So I probably let me put 2's under here because those are the time for the second half of the race. So I put this all together, the total time equals T1 plus T2, which is 12.58 seconds. That's a pretty good time. Okay. Let me zoom out here again so you can see the whole problem. All right. So you could freeze frame the video here if you want to review this later. And I'll switch back to webcam. No Newton's law on that problem. It's just a kinematics problem. I just threw it in there to, so you don't forget that these tools are in your toolbox. Kinematic equations of motion. All right. So, let me see. I don't see any questions in the comments, so let's keep going. Next thing I want to talk about is, let's talk about this conceptually first, okay? And then we'll proceed to writing out a problem and doing some physics to get some deeper understanding. So there's a homework problem that is related to this scenario. Let me show you that. So it's this problem about the gymnast. You guys, I don't know if they still do the rope climb in gym class. Do they still do the rope climb in high school gym class? Because we did that in high school, and when I think about it now, I can't believe they let us do that. We would climb up this rope to the top of the gymnasium, like, what, 30, 40 feet up, just holding on, and then come back down. This girl, they did that in my middle school. So they still do it somewhere, I guess. The girl climbed all the way to the ceiling. They don't do it. Talk about liability issues. That's a shame if they don't do that, because that was a heck of a lot of fun. I really enjoyed the rope climb. Anyway, I'm getting distracted. This is a gymnast, so not just a high school gym class student, and you're given Kevin's mass, and the gymnast climbs this rope, and the first part is, Kevin's weight pulls down on him, and what keeps him up is the rope exerts tension. So tension is a kind of force. Tension is a kind of force that's directed along things that can support tension. Ropes, chains, lengths of wood, anything that if you pull on it resists. In the first part there, the question is, well, what if you have a constant speed? Kevin's going up at a constant speed. Another name for constant speed is zero acceleration. And in part B, it's, well, what if he's accelerating upward? And so we're gonna consider the physics of what's going on here, but we're gonna look at a different scenario. The scenario we're gonna look at is a guy in an elevator, or a girl, a person in an elevator, and this is physics-wise very similar to the rope climbing problem in your homework. All right, so we'll proceed by, I'll draw a picture, and I'll draw a free body diagram, and then we're going to apply Newton's second law to the picture that we draw, and see what happens in different scenarios. Okay. Come on. All right, I guess that'll do. Trying to clear the whiteboard. It doesn't like me to push everything off the page. It likes to keep a little bitty piece of it there. All right, so let's call this elevators, and the phenomenon of apparent weight. I am such a bad speller. I don't know if I spelled any of this right. Elevators and apparent weight. All right, that's what we'll call this. And let's start with drawing a picture. So elevators are kind of box-like. And there's just one person in the elevator. And let's try those legs again. There we go. One person in the elevator. And there's usually cables up here that are keeping the elevator up, and the elevator's in an elevator shaft, but we won't draw that. And so let's try to identify the forces acting on the system. Okay, so elevators, oh gosh, oh, that's so bad. Elevators. Elevators. Okay, so help me out here. In the comments, tell me what forces I should draw on this picture. I'll use blue to draw the forces. I'm going to draw arrows that represent the forces acting on this system. Alright, so I'm looking at the comments. You tell me what forces act. So Holly says gravity. Maddie says normal force. Okay. Alright, so I'll write that. So a question that you have to answer first is William says I should just use the word lift instead of elevator. Easier to spell. The thing you need to answer first is the question I said is, what are the forces acting on the system? And in this case, in all cases, you should say, well, what is the system? And is the system the elevator? Is the system the person? Is the system the elevator and the person? And in this case, we want to focus, so what we want to gain some understanding about is the experience of riding an elevator. So that suggests that what we want to focus on is the person. We want to think about the forces acting on the person because those things will influence the experience that person has. So in this case, our system is one object, the person, and we want to identify the forces acting on that person. Okay, so you guys got it. Holly and Maddie, you got this. So there's the force of gravity. I'll call that W for weight. Remember, weight is synonymous with the force of gravity. And last time we analyzed this a little bit and discovered that the weight of an object near the Earth's surface is its mass times g, the acceleration due to gravity. And then there is a normal force. I'll call that N, and that's directed upward. That's the floor pushing up on the person. And if we expand the system, there's other forces here. There's a tension. I'll draw this in red because they don't apply in this case, but there's a tension pulling up on the elevator cable. And then, of course, there's the weight of the elevator itself, which is pulling down. But those are forces that are not on our object of focus. All right. So our object of focus here is the person. Let me draw this a little bit more simply. That dot is the person. And my free body diagram for that person has one vector pointing up for the normal force and one vector pointing down for weight. Okay? And when I approach this problem, I'll call up positive and down negative. Okay. And we don't know anything about, we haven't said anything about what the elevator is doing. But if you think about it, there's three possible, well, I guess from a Newton's law perspective, there's three possibilities, but I guess one of those possibilities is sort of two different realities. What I mean by that is one possibility is the acceleration could be zero. And what does that mean? That means that if the acceleration is zero, the thing is at rest, or the thing is moving with constant velocity. Okay, that in either of those cases, acceleration is zero. Acceleration being zero means v isn't changing, so it means it's got to be constant. Well, zero is a constant. That's a possibility. Another possibility is the acceleration is greater than zero, so that's accelerating upward, because I said up is positive. And a third possibility is acceleration is less than zero. That's accelerating downward. Okay. And so now let's apply Newton's second law to this situation. Newton's second law says the net force on this person is equal to, I put an m there because the person has a mass, times the person's rate of acceleration. That's Newton's second law. Net force equals mass times acceleration. Well, in this case, the net force, net means total. I'm summing up the forces, and there's two of them. One is positive, because I called up positive, and the other is negative, because I said down is negative. So the total force is the normal force minus the weight. Okay? And those two things must be equal to one another. So the normal force minus the weight equals mass times acceleration. So we can think of this equation here as, it's kind of like a master equation to describe this situation, this system, consisting of one person in an elevator. It's the master equation. The equation of motion. As physicists use that word a lot, equation of motion. And it relates forces with accelerations. So let's see what these possibilities up here result in down here. All right. So in situation one, if a equals 0, what we have is the right-hand side of this equation is 0. So we get n minus w equals 0. What does that mean? N equals weight. Okay, if a is greater than 0, we would have n equals weight plus mass times acceleration. So if a is greater than 0, that means the normal force is greater than the weight, because you're going to be taking the weight and adding something positive to it. And in the third situation, if a is less than 0, you'll have n equals w plus mass times acceleration. So if a is less than 0, you're going to take the weight and subtract off something, because the second term will be 0. You'd have n is less than the weight. So you have these three situations. Okay, these three situations, and now let's talk about what the experience is like on an elevator. So you're on an elevator. Let's say we're not spending a lot of time in Bird Science Center this year, but there's an elevator in Bird Science Center. You get in on the ground floor, and you push the button for the second floor, and you start moving upward. And in order to move, you got to accelerate, because you're starting from rest. And what does it feel like in those first couple moments that you're accelerating upward? What do you feel? I'm looking at the comments. Tell me what it feels like. You feel a force pulling you down, being pulled down. So what force is always pulling you down? Like you're being dragged downward. What force when you're on the Earth's surface, what force always pulls you down? Gravity. Good, William. So one way to interpret this experience, gravity is your weight. So one way to interpret this experience is it feels like you weigh more. It feels like you're way more while the elevator is accelerating upward. That's in other words, the way it feels would be identical to if you were transported to another planet where gravity was stronger. It would feel exactly the same as those moments where you're accelerating upward. And so we can call this your apparent weight. Your apparent weight seems to be larger than your actual weight. And so here's one of the truths about the situation. Gravity isn't getting stronger just because you're accelerating upward. So while you feel heavier, you aren't actually heavier. Gravity is still pulling on you in the same way. So your actual weight, W, doesn't change, but the sensation of weight does change. Okay, so so this leads us to the thing in this problem which actually gives us the sensation of our weight. Let's go back to this picture here. Look at this picture here. We got two forces, a normal force pointing up and the weight pulling down. And one of those forces is our actual weight, W, and the other one, the normal force, is the thing that gives us the sensation of our weight. Okay, so we're not actually feeling our weight. What we're feeling is the floor pushing back on us. That's what gives us this. It's like you're sitting in a chair right now. You don't feel gravity. Gravity's acting on you. What you feel is the chair pushing up on you. So your weight pushes on the chair, and the chair pushes up on you. Okay. So in this problem, what we have is we can think of N, this normal force in this situation, as being equivalent to our apparent weight. Okay, not what we actually feel, not our actual weight, but what we appear to weigh. And close that. So what we have is over here in the first case, where you're not accelerating, you appear to weigh what you actually weigh. The normal force is the same as your weight. In this scenario, when you're accelerating upward, your apparent weight is greater than your actual weight. You feel heavier. And in this scenario, so this is like you get in the elevator on the top floor, hit the button for the lobby. The moment you start accelerating downward, you feel lighter while you're accelerating. And that is, your apparent weight is less than your actual weight. Okay? So once you accelerate for a while in an elevator, if it's a tall building, and then you start traveling at a constant velocity, everything returns to normal feeling. So if you're moving with constant velocity, that's zero acceleration. Your apparent weight is the same as your actual weight. And you think about, well, what is the extreme situation? The extreme situation would be, what if you're on like the top floor and the elevator the cable snaps, and then you're in free fall, and when you're in free fall, the force of the floor pushing up on you is zero, so you feel weightless. You feel weightless. You're not actually weightless because gravity is still pulling on you. That's why you're falling, but you feel weightless. And this is what astronauts in Earth orbit experience. They're not actually weightless, but they feel weightless because they're in free fall. They're falling toward the Earth's surface while they're moving in a circle. Okay? So there's a difference between um, what we, the thing that gives us the sensation of forces is usually not the force itself, but something reacting to that force, which in this case would be the elevator floor pushing back on us. The same is true of a bathroom scale. What is the bathroom scale actually measuring? It's measuring a normal force between your feet and the surface of the scale. If you put the bathroom scale in an elevator and the elevator starts accelerating downward, it'll tell you, the bathroom scale will tell you weigh less. You don't actually weigh less, but the apparent weight that you have is less, because what it's actually measuring is the normal force. Same thing, if you're on the bottom floor and you start accelerating upward, and you're standing on that bathroom scale, it'll tell you you weigh more, even though you don't actually weigh more. All right, so weight is synonymous with gravity. Weight can be calculated as mass times g, the acceleration due to gravity, for objects that are near the Earth's surface. And one other thing to take away from this problem here is key. When you're using Newton's second law, in situations where acceleration is not zero, so it could be positive or negative, but not zero, that happens because you have unbalanced forces. In this case, all the forces are balanced out. The total force is zero. And that results in acceleration of zero. So anytime you have, and this is really key. This is like very, very key to understanding Newton's law. Whenever you have an unbalanced force, an unbalanced net force, so a net force that adds to something that's not zero, that's when you have acceleration. That's what causes acceleration. Non-zero net forces cause acceleration. All right. Looking at the comments, let's see here. Don't see any questions. Okay. So let's continue. We got 13 minutes. I think we can get pretty far into this next situation. Let's keep working our way across. Come on. Keep working our way across the page here. Okay, so what I want to consider now is, let's consider the physics of a cart rolling down and we're going to assume it's a frictionless incline track. And all right, so we have a track that's inclined, and you can describe that incline as an angle called theta relative to the horizontal, and then the cart is on this track and it's accelerating down the track. Okay, it's accelerating down this inclined track. And so now, what forces? Acceleration is not a force. So that's I drew it on here because I'm showing the direction the cart is rolling. Acceleration is not a force. Acceleration is the effect that a net force has. So I'm looking at the comments. Tell me what forces act on this cart. There's no friction, so we can ignore friction. And tell me what forces act on this cart. And I'll draw them in. So we got gravity. Okay. Gravity. What direction does gravity point? Straight down. I think let's draw it like this. Gravity, weight, points straight downward, right? So even though it's on an incline, all right, and that can't be it. Okay, Steve says normal force. All right, so in this case, you gotta be careful. The normal force, normal means what? In geometry, normal means perpendicular to. So when I'm drawing the normal force here, the normal force is perpendicular to the surface. All right, so I'm going to draw a free body diagram a little bit more simply here, just to focus on these two forces. So I have the normal force, and I have weight. Okay. And so we already, whoa, that was weird. Okay, we have a come on, there you go, two-dimensional problem. And we know it's two dimensions because the vectors don't line up with one another, so we got to use two dimensions here. And you know, there's two natural choices for my coordinate axes here. I could say, well, up is positive y, down is negative y, and then, you know, left and right are positive and negative x. And in this case, that isn't actually the best choice for my coordinate axes. It is a better choice to sort of rotate my coordinates so that x, positive x, is along the direction of motion, parallel to the surface of the incline, and positive y is perpendicular to the incline. Okay, so if I come over here to my picture, I'm saying, you know, the y-axis lines up with the normal force, and the x-axis, well, why is that moving on me? Is parallel, or sorry, perpendicular to the normal force, parallel with the track. All right, and I'm gonna keep my eye on time here. One thing we know is, if you think about, well, let's not actually, you know, prove this. You can prove it to yourself. The angle, when I draw my axes like this, the angle that the force of gravity, weight, makes with the y-axis is equal to the angle of incline of this track. And you can imagine, well, if the angle of incline goes to 0, that angle goes to 0 too, and the y-axis is vertical. So with these coordinate axes, the object's weight has a y component and an x component. There's a y component and an x component to the object's weight. Zoom in a little bit there so you can see that. Okay? So in this type of problem, it's a two-dimensional problem. What was the strategy we used for projectile motion when we had two dimensions? We have vectors in two dimensions. What was our strategy? What did we do? You know, so in the exam, some students didn't do this very well. What they would do, I'd see an equation and it would have terms in there for like x displacement, and it would have terms in the same equation for y acceleration. And that's a big no-no. You don't want to do that. What was the framework that I laid out for you guys? You have two-dimensional problem, and you split it into x and y components. Okay? The strategy here is exactly the same. So in this problem, let's look at the y direction first. In the y direction, we'd use Newton's second law in both of these directions. So we write down an equation of motion using Newton's second law in the y direction. The net force in the y direction is, well, we got that normal force, which is pointing up. We said that was positive. And then we got a y component of gravity pointing down. And that net force, Newton's second law, is equal to the mass of the cart times its rate of acceleration in that dimension. So we put these together and we get that the normal force minus the y component of gravity is equal to the mass of the cart times its rate of acceleration in the y direction. Well, what is the acceleration in the y direction? Is it accelerating perpendicular to the track, or is it accelerating parallel to the track? It's not accelerating in the direction we called y direction. It's not accelerating perpendicular to the track. So that is 0, which means the normal force is balancing the y component of gravity. You know, what is that anyways? If we go up here and look at this picture, what is the y component of gravity? Well, you know, the total weight is m times g. The y component would be that times cosine of this angle. So here in this case, you know, cosine is adjacent over hypotenuse. So here the y component is adjacent to the angle we know. So the y component of gravity is the weight times cosine theta. And the x component of gravity is weight sine theta, because in this picture the x component of that gravitational force is opposite the angle theta. Alright, so that means the normal force equals mg cosine theta. Alright, so you think about this, if the track were flat, you know, if the track were flat, theta were 0, what's the normal force? Well, the cosine of 0 degrees is 1. So that maximizes the normal force, and and then it's equal to the weight. So if the track is flat, the support that the track is exerting on the cart is equal to the weight, just like in the elevator when it's not accelerating. What if the track is perfectly vertical? At 90 degrees, cosine of 90 degrees is 0, so the normal force would be 0 in that case. That's free fall. All right, well, let's go to the x direction and finish up here. So in the x direction, we have the net force in the x direction equals, well, there's only one force in the x direction. It's the x component of the weight. And Newton's second law says that net force is equal to the mass of the cart times its rate of acceleration in that direction. And really, that's what we have here. We have acceleration down the track. So we put those two things together. That's mg sine theta, and we have mass times acceleration equals mass times g sine theta. And an interesting thing happens here. The masses cancel. The mass of the cart doesn't matter. And you have the rate of acceleration equals g sine theta. So this formula should look similar. It was in your lab last week. And you know, one of the things that it's telling us is that it's kind of, you know, if you think about, you know, the physics that we're talking about here is similar to the physics of roller coasters, and it's a good thing that our answer doesn't depend on the mass, because if it did, your roller coaster would behave differently depending on how many people are in it. And in the real world, it does behave differently if it has more, if it's fully loaded versus mostly empty. because friction is a factor, and there's other things. But to this first approximation where we're ignoring friction, and you certainly design roller coasters to minimize friction, the way it accelerates isn't a function of the mass of the roller coaster. And if because that's true, you can design a roller coaster that behaves pretty much the same regardless of how many people are on it, and that's what makes them possible. So, okay, so that's it for today. All right, so here, let me show you this one more time. All right, leave this up here for a second so you can pause the screen if you need to, if you're studying this. And later this week, we'll take a look at what happens in this situation when friction is playing a role. So that would be like the physics of a kid sliding down a sliding board. All right, so until then, look for your exam scores posted later today, and I will see you guys tomorrow at 1:50 for lab, and we'll talk about that, and then on Wednesday. All right, take care.